Last thing we had actually talked about was an example where we are trying to decide increasing, decreasing behavior and all that. And again, I want to reiterate, the book has some mistakes in it. So what we want to do is remember that we have to use the parentheses for those, because a point cannot be either increasing or decreasing. So we just use our open brackets for these. And this says for each function, tell the intervals on which it is increasing and the intervals on which it is decreasing. And my hope would be that we really don't even need to grab the graphing calculator when we see something like this. That we would remember, okay, x plus 2 squared. Wait a minute, that's going to be a parabola. And where's this parabola going to go? Well, if we remember that the x is always the opposite of what we see. So normally we'd say, hey, that's going to be 2 to the right, but the x's are always backwards of that. So we're going to go to the left. And that means that our parabola has a vertex right here. And it's going to look like that. And that's really all we need to talk about decreasing, increasing behavior as we go through that. So as we look at this, we can see there's part of it that's going to be going down, there's part of it that's going to be going up. So decreasing, we'll want interval, and increasing. We read graphs from left to right. So on what interval is this decreasing? Draw over the top of it. Start up here. If you're moving down, we're decreasing. We're decreasing till we get right here. Again, always the parentheses. All right. Well, then what's the rest of it doing? Increasing, because we go up. We've got it. We didn't have to grab a graphing calculator for that. Obviously, we have not reviewed here while introducing you to a wee bit of calculus. Wee bit. All right, so here's what we do. We say, we've already talked about the denominator stuff and how, you can't have that be 0. Okay, so I look at that and I realize I'm going to have a couple of asymptotes. They're going to be at -1 and at 1. So I definitely get the feeling here that we're looking at a 3-part hyperbolic function. Now, it's hyperbolic because we have division. Whenever you have a ratio, you're talking about hyperbolas. So now I think, I wonder if there isn't a cutoff to this that goes horizontally. So here's how we do this. We say to ourselves, really, as this goes to right and left forever, we're really thinking about this in terms of infinity. So what we want to see is what would happen if we put infinity into both of these positions. What would this graph be doing? Would it be approaching something as you go to the right forever, as you go to the left forever? So instead of x, I kind of use infinity as if it were a variable. Like that. And now, here comes a little bit of calculus thinking that we need to have. A little bit of calculus thinking is this. And I'm going to give you a story for it because it makes sense in the end. You're a person who loves the environment, big on the environment, and you hear that the waters of the ocean are actually going down. So every day when you get up in the morning before you go to work, you go out to the ocean and you stand right there next to the water and you spit in the ocean and you say, look at how much water I've just added to the ocean. Didn't I do good? Have you really added anything to the ocean's problem? Nothing. That -1 down there is spitting in the ocean. If we are talking about infinity, is a -1 going to do anything to infinity? Absolutely not. So we don't even think of this -1 because that's spitting in the ocean, it's nothing. We think, what would happen if that were out of there? Because it doesn't matter, it's gone. And we treated this as if it were a variable. What would happen to infinity squared over infinity squared? It would be 1. That is our horizontal asymptote. Y equals 1. Now without a graphing calculator, I could just quickly make myself a little sketch by just making even the smallest tables here. The smallest tables. I have 3 parts to this graph, and I look at it and I say, well, this is cut off right here at x equals -1, so maybe if I put a -2 in, I'll know whether or not this is above or below here. So I just quick take a -2, plop it up here and see what I get. -2 squared would be 4. -2 squared is 4 minus 1, so I get 4/3. That's enough for my sketch, because it tells me at -2 the graph is going to be at 1 1/3. Which is above my asymptote up there. Then I need something from the middle. Hey, I love 0. I like working with 0. So if I put 0 in here, I'm going to get 0 over 0 minus 1, which is 0. 0, 0. Now, it could be, we've encountered this before, that our horizontal asymptote might not work in that middle section of the graph. We could have an S-curve in there, bless you, we might not. So at this point, we could put in another number like a half and just take a look at it, but right now we know it's at 0, 0. So if we put a half in there, even a 0.5 if you wanted to use your graphing calculator, 1/2 squared is 1/4 over 1/4 minus 1. So that's going to be, I'm going to have to go this way, 1/4 over 3/4 multiplied by the reciprocal. Let's see what happens. So 1/4 over 1/4 minus 1 will give us -3/4. Flip it. What are you going to get? Got 1% down. Okay, so -1/3. Now that's really all we need. And that's too low, I know, but really all we needed to know was, is it going to start back down or not? Now, if your argument is, do we need the -1/2 here so that we can see it? Yes, I agree with you. But you can see with just a few points, we can figure out what's going on. And then we'll go over here to 2, and we'll see if that's above or below our asymptote. Pretty good bet it's going to be above. Kevin? No, it won't. We'll talk more about that as we go on. So if we put a 2 in here, this will be 2 squared is 4 over 4 minus 1. So we get 4/3, which is 1 1/3. And we know we're back up here. And to talk about the increasing and decreasing intervals, that's all we need is a sketch like that. Now, like I said, we really probably should put a -1/2 in here. And that way we'd know for certain that that's coming back down. Or you can grab a calculator, because right now we're saying, hey, we don't have all the pieces quite together yet. We're going to get there. So what we need to do is talk about decreasing and increasing and all that good stuff. Now I say all that good stuff because does this graph have a constant? Do we have a spot where everything's flat? No. Okay. So decreasing and increasing. I know I didn't give myself enough room here. So let's go after decreasing left to right. Let's see what we can find. Well, as we draw this graph, this is all increasing. It's pulling away from the asymptote and it's increasing. On this side, I'm increasing, but then, There we go, there's a decreasing. So how are we going to represent this decreasing interval right there? 0, 2, 1. This is going down from left to right, so we're also going to have to represent that as decreasing. So what should we use for the interval for that one? 1 to infinity. Now let's go back and grab our increasing if we didn't already write those down. I guess usually when I do these, I just start left to right and write them down as I go. But this was definitely going up, so what's our interval for this piece? Negative infinity to negative 1. Any other part where this graph is going up? Yep. Oops. Here it is. We break that into pieces so we can see what's going on, and those pieces are called intervals. We look at them over an interval. So down here, what we want to talk about changes gears. This is about a concept called boundedness. Boundedness means there is a cutoff up and down to this graph. Now, it can be just bounded above, just bounded below, but if it's both, you say it's bounded. So, we look at this first one. And, again, they're giving us graphing calculator shots. We know those are supposed to be arrows there, but this is continuous, going to continue on. So not bounded above, not bounded below, because these arrows are saying, hey, we're going to keep going forever up there. These arrows are saying we're going to keep going forever down here. So it's neither bounded above or below, and that means it can't be bounded, because to be bounded, it has to be both. So now I look at this one, and I realize there should be arrows there. So this thing's going up forever. But there is a lowest spot down there. So I could draw a horizontal line that it would never touch. Get really, really close to it, but never touch. So this is bounded below. It does have a line that we could represent, hey, it doesn't go any further than this. This one, we put our arrows on there. We see, hey, this is going down forever. Nothing we can do about that. But does it go up forever? No. That would be bounded above. We could put a line up there that it's never quite going to reach. And then this last one. No arrows. Notice, to show us that, they made some big black dots there and said, boom, done. Both above and below. Bounded. So it can be bounded above, it can be bounded below, but if it's both, then we just say bounded. And if it's neither one of them, then you just say not bounded. No, it's not. So lower bounds and upper bounds and bounded. A function f is bounded below if there's some number b that is less than or equal to every number in the range of f, and any such number is called a lower bound of f. That's the line. You know, you draw a line y equals b down there, and you know, it's just not going to quite make it there. A function is bounded above if there's some number b that is greater than or equal to every number in the range of your function, and any such number b is called an upper bound of f. So the line that's just a little too high, the graph is never going to reach it. And then if it has both, it's called bounded. Make sense?
Would you use lower and upper, or would you use below and above?
It doesn't matter. As long as you can check it in the back, you're really saying the same thing. You know? So it doesn't matter if we say bounded above, bounded below, or if we talk about an upper bound and a lower bound as we go through that. So now we can extend our boundedness definition to the idea of bounded on just an interval. Oh gosh, what are they talking about now? Well, let's go back here. the slow of the day. Right there. If I just look at this graph in between my two red vertical lines, is this portion of the graph bounded? Is it bounded above? Is it bounded below? Is it bounded above, right? It does have a highest point. So now they're saying, instead of looking at the whole thing, say, well, from this number to this number, that part is bounded above. And that's what we're going to do. So I'm going to kind of chop this up just like we had to do when we were talking about decreasing and increasing. So extend that idea, bounded on an interval, by restricting the domain, saying just for these x's right here. And it says the domain of consideration in each part of the definition to the interval that you wish to consider. And they'll tell us what interval we should be looking on for. So for example, the function f of x equals 1 over x is bounded above on the interval from negative infinity to 0. Well, we better see that. We see the division. We're thinking hyperbola. And we're looking around saying, well, do we have a vertical asymptote here? Do we? Is there a bad number? 0. Will it have a horizontal asymptote? As we go to the right forever and as we go to the left forever, will we have something that it is going to approach? We need to think about this as if it were infinity. So as I go from 1/2 to 1/4 to 1/8 to 1/16 to 1/32, what is this getting closer and closer to, but it's never quite going to get there? It is 0. It is 0. So that's going to be our horizontal asymptote. There it is. So now, you think there's stuff going on the right, there's stuff going on the left, I can't use 0, maybe I'll just use 1 and 2, get a couple of nice numbers. 1 over 1 is 1, 1 over 2 is 1/2, so 1, 1, and 2, 1/2, and it makes sense that our graph is going to do this. Because that's what asymptotes tell us. They tell us it's approaching it, but it's never quite going to get there. And if we put -1 and -2 in here, we get -1, -1, and -2, -1/2. Well, you can memorize, and that's what a lot of teachers will have you do, is memorize it, but you might not hold on to that information forever. So what we want to do is start thinking of this. In fact, this is what Mrs. LaRue told us last year to do, was make sure that we explain this in terms of limits, so that you can start getting that now before you go to calculus and start thinking of it that way. Yeah. So now, we have our graph. And they want to know, it says the function is bounded above on the interval of -infinity to 0. Does that make sense? Bounded above, right? Bounded below on the interval from 0 to infinity. Do you agree? Yeah. So if you do say, hey, just from here to here, what is this graph doing? It makes a difference. We can't say bounded above and bounded below for this whole graph. That's not going to work. But for pieces of it, absolutely. All right, so down here, checking boundedness. Identify each of the functions as bounded below, bounded above, or bounded. So start thinking about what this looks like. And x squared is a parabola. 3x squared means it's going to go up a little steeper. But then I see the -4 tells me what? Down 4. And I realize, isn't that really all I needed to know? Because I know it's a parabola. This is going to look like that. Bounded below, bounded above, or bounded? Bounded below. There's a cutoff here. Bounded below. Division. What does that tell me about the second one? Hyperbolic of one kind or another, right? Okay, but we got some weirdness going on here because I'm looking at this denominator and I'm thinking, when could that be 0? I'd have to subtract 1. Are we going to be able to graph that on the Cartesian coordinate plane? No, because that's imaginary. Okay, so basically we're not going to get any vertical asymptotes. All right, good to know. Okay, horizontal asymptotes. What's that one? Spitting in the ocean, right? Not going to matter. You'd cancel 1, right? It's 0. Because if this keeps going, we're approaching 0. But we have to remember, vertical asymptotes set in stone. Set in stone. Vertical asymptotes we will never cross. Horizontal asymptotes are always a maybe. We don't know until we get it all done. Now we could make a table with this one, but I think this one is more effective when we just look at it on the graphic calculator and see what's going on. So we're going to have x divided by 1 plus x squared. And I'm going to do zoom 6, negative 10 to 10 window. Oh my, right? Really? That's all we get? No. We could try messing with the window a little bit and hope for the best here. Maybe we stretch this out. We look at that little piece in the middle there from negative 2 to 2. So the question is, does our horizontal asymptote work with this one, or does it go through 0, 0? And that question can be answered really quickly by just putting a 0 into this function. Crosses it, doesn't, and that happens sometimes. It just does. So let's get our sketch on there. So, what they wanted to know about these. Bounded below, bounded above, or bounded? Bounded? Now we're going to take this a little further with some algebra. It's not enough that we just figure out bounded below, bounded above, bounded. I think anybody can punch it into the calculator and get that piece for me. But here's what we would want to know. How do we start here and end up by knowing where this is going to be bounded at? And here's how we start. We say, what I recognize about this is x squared. And I know that x squared will always be greater than or equal to 0. But what I need to get is 3x squared minus 4. So I think, how can I build this up so that the left side would say 3x squared minus 4? Well, what I would have to do is multiply both sides by 3. And then I'd have to subtract 4 from both sides. Take a look at our graph. Was our graph greater than or equal to negative 4? It sure was. sure was. That was our lowest point. So kind of using algebra backwards, we can see this is going to be bounded. We build it up from x squared to 3x squared minus 4, and we get that piece. Now, it's kind of similar for the other one, but I could see some people kind of glossing over about that piece. So maybe I'll come back to that after 5 if we have time to do the algebra with that. But what we did notice on this one, it was actually where I was going to go right away, was everybody know how to find those from last year? Yeah, our local maxes and our local mins. And that's the part that's always disappointing, is because we have to use our calculator for those. Without knowing calculus, which you won't know until next year, we have to use our calculator to find those. Those are our local maxes and local minimums. So local and absolute extrema. And what we're seeing here is a basic graph, and we're seeing, hey, there's a high point if you just look at this interval. That's going to be called a local max. There's another one right here. So those are local maxima. But this little bugger down here at Q, if you just look at this little window of interval here, that's a local minimum. So local max, local minimum. And what we want to do is get used to writing these as the maximum is, and then telling them the y coordinate, at x equals the x coordinate. So maximum of 5 at x equals 2. Things like that we want to say. In this case, we probably have 4, 1, 2, 3, 4, 5. Max of 5 at x equals 4 for r up here. So when we write those, it's almost like a sentence. You know, we're kind of putting it all out there so people can see it. So local maxes and local mins. And we do have a definition. A local maximum of a function f is the value f of c that is greater than or equal to all range values of f on some open interval containing c. So from here to here, is there a high point? That's your local max. If f of c is greater than or equal to all range values of f, then it is a maximum. And if it's greater than the entire graph, it's an absolute maximum. Think parabolas. Parabolas have an absolute lid to them, upside down parabolas. There's an absolute maximum for parabolas. But when we get to cubics, we might see some lumpy bumps in there that give us local mins and max. A local minimum of a function f is a value f of c that is less than or equal to the range values of f on some open interval containing c. If f of c is less than or equal to all range values of f, then we're talking about the local min will become the absolute min, the lowest spot on an open parabola. And local extrema are also called relative extrema. In case when we switch books for the calculus there, those are a little bit different. So local maxes, local mins, you guys have done that on your calculator before. And this one says decide whether f of x equals x to the fourth minus 7x squared plus 6x has any local maxima or local minimum. If so, find each local maximum value or minimum value and the value of x at which each occurs. Overall, what does this equation look like? Talk to me about n behavior. Fourth power, positive leading coefficient. It's going to be parabolic. So what we're going to see is out here somewhere it's going to go up, and out here it's going to go somewhere up. Because whenever we talk about the even degree polynomials, they're going to be parabolic. But what we don't know about yet is what's going to happen in between. Because it's not just x to the fourth. There's some lumpy bumps taking place there. So yeah, we're going to grab a graphing calculator for this one and just get it up there. X to the fourth. 7x squared plus 6x. Go back to my Zoom 6. Looks like so. Might want to window out a little bit here. Get a little bit lower in my y's. Right, so all I did was change my y min to -30. Because in order to find it, Blinky has to be able to see it. And he can't see it if we can't see it when we hit graph. So we have to see those. So a quick sketch would have us doing, I don't want to make this so wide. Something along those lines. So we first would identify, hey, we've got what look like 2 local minimums right there. So local min of blank at x equals blank. And then we have a local max, which is probably more over here. Calculator time. Just is. So second trace, and number 3 is the minimum. And I just usually go left to right. You just want to find one way to always do this. You'd be on the left side of the valley and hit enter, and then move Blinky to the right side of the valley and hit enter, and enter to guess. So negative 2.057 is our x. Three decimal places, always 3 decimal places. Negative 24.057. 3 decimal places. And then we've got maximum coming over here. Left side, right side.
Original and rewrite it.
There's three of us that come up with all this stuff, and for me, this is not a big deal, you know, and that's because my minor was in economics, and we use the X and the Y, and we use them in a lot of different ways. But the other 2 teachers, if you don't write it in this form, they're going to get you. They're going to dock it. You know, they like this form. This is the way that they do. But like I said, in a lot of fields, you will use this, either the X or the Y. Neither one of these is more important than the others. But they want to see that that Y value for the max or the min is there first. That's the reason that they do it. So we decided we'll just all do it that way. So if some of you have one of them next semester, I'm not messing you up by saying you don't have to write it that way. So I've got my maximum at 0.45. So I'm not going to make you rewrite it, but know that the next time you do it, you know, get used to that. I suppose while I was yakking there, you probably already had this last one. All right, local max, local min. 43210 me on just how you feel about the local max, local min thing. Everybody remembering all the things that they need to do with those? Okay, some people not feeling quite as good about it as everybody else. So remember, we just lead Blinky where he needs to go. You know, if we have a valley, we're going to go to the left side of the valley and hit enter. Go with the arrows to the right side, hit enter, then just hit enter to guess. We don't need to take a guess, and it will get it for us. For the maximums, left side of the hill, press enter, right side of the hill, press enter, enter to guess, it'll get it for us. Cassie, did you have something else? No? Okay, I thought I had seen your head. No, I was explaining something. Okay. So now, Another really good concept, like we haven't had enough in this section, is symmetry. So symmetry, we can have what's called even symmetry. Even symmetry means that the y-axis is the axis of symmetry for our graph. But if we're not allowed to graph it, like maybe if somebody took your graphic calculator away, could you figure out by algebra whether or not we have an even function? So a function that has the y-axis symmetry will do this. If you put a negative x in wherever you see an x and simplify it, it will look exactly like the original function did. And that's because of that symmetry. We're really saying, all right, when you take this and you use it for a reflection across that y-axis, what's happening is your x are becoming negatives, but you get the same answer because all of these values for y are going to be exactly the same. Over here, this one is odd symmetry, an odd function. A function that has origin symmetry, which is 180-degree rotational symmetry, and that's different. If you put a negative x into that, what it should do is it should negate your entire function at the beginning. You should see exactly the opposite as what you started off with. So with this one, if we put negative x into the function and we simplify, magically we get right back to the beginning. Everything's good. With this one, we put a negative x into the function. When we get done, we see the exact opposite function that we started off with. If it's not one of those two, then we don't say that it has symmetry. In fact, it might even have symmetry, but not one of these two, not y-axis and not origin symmetry. So, sorry, Cass. Even and odd. Only choices we're going to get. We might see, you might say to yourself, gosh, that looks like it has symmetry at y equals 1, but we're not allowed to think about that right now. It's just even versus odd. So this one has us checking functions for symmetry and tell whether each of the following functions is odd, even, or neither. We're going to look at it graphically, obviously, but then we're also going to confirm this algebraically. So take a peek at that. Even or odd? Yeah, I mean, you can see right there, flopping over the y-axis there. So, even. Here's what that means. We have this as the original function. Wherever we see an x, we're going to put negative x in for it. What happens when you take negative x and you square it? Just becomes x squared. Has to be. Even as the y-axis. Yeah, always, no matter what. So, how does this compare to this? So it's even. That's how even works. You put the negative in, you simplify it. If it's exactly the same, bam. Now, is this odd? Everybody look at it. Is it odd? Okay, so how are we going to know that? Well, the same way. We look at this and we say, hey, we put the negative in. If this were odd, it would look like this. Everything should be the opposite sign. But it's not odd. Because it's not. It didn't work. So algebraically, we substitute a negative x in and we see what happens. How about that little bugger right there? Even, odd, neither, neither. So now we'd have to confirm that algebraically. We'd say, all right, g of x starting looking like this. And if we put a negative x in, and simplify it, the first thing we do is we compare it to the original, ask ourselves, is it the same as the original? So it's not even. And if it were odd, we would have the opposite of everything that we see. Is what we had in the green, negative x squared plus 2x plus 2. No, so it's not odd either. Put the negative x in for x. You simplify. If you get the same thing you started with, it's even. If you get the opposite of what you started with, then it's odd. That means it has that 180-degree origin symmetry. None? Definitely not even, right? Okay, so let's check it out. Bless you. Negative x cubed. What do we get? Square it first, order of operations. Then put the negative in front. It's not even. Is it odd? Is this the opposite of this? It is. It is. And what we could do, remember, the negative goes in one position. It either goes in the top, it goes in the front, or it goes in the bottom. So we could pull it out front, and then it would be obvious to us, oh yeah, exactly. So it's either the top or the bottom that we're going to see that negative in there, but that's going to be our odd piece. Right there. So it's either in the top, or it's in the bottom, or it's out front, and then we can see it. So down here we have determine algebraically even, odd, or neither. And thought we'd at least get through. Let's give it a try. Let's take a look at A. What are you going to do? Even, odd, or neither? Even. Even, odd. It's not exactly the opposite of everything, and it's not exactly what we started with. Which is it, everybody? Is that odd or is that neither? In order for it to be odd, everything would have to be the opposite, because this is not a fraction. With fractions, it's pulling that negative out in front, but with this, it would have to be the whole thing. So that one's neither. And that's a good place to stop. They get a little weirder after this. Actually, the next one would probably be okay, but let's not do the weird. Okay. I don't have anything new for you for assignments. It's just piecing together the assignments we already have. Taking a look now at that yellow worksheet, starting to think about using infinity to figure out if you have any horizontal asymptotes.
Do you think we're going to be able to do it on day 3? Wait, we have to be on day 3.
What haven't we done yet? I kind of talked you through the asymptotes piece, but we need some more time on that one. So
finish day 2.
Probably finish day 2.
Just finish day 2 and do the yellow worksheet?
Yeah, if you can do the yellow worksheet now that we've talked about those asymptotes, you should be okay. The 42 to 46 even, that's local max and min. You can definitely do that now. 47 to 54 is odd and even, so you could do those. You might want to hang on to 55 to 62 because, like I said, I touched on horizontal asymptotes, but you haven't done a lot of that.
So we can do 42 to 46.
So we can do like the first half of day 3.
You could get through 54 easily at this point. 54 easily. And maybe some of the review ones at the end. I was thinking you guys had questions.
Congrats.